has come, I guess, it's my pleasure to introduce the third plenary speaker of today, Luca PAVARINO. Luca PAVARINO is a full professor of numerical analysis at University of Pavia in Italy, and is a very well-known expert in numerical modeling, in particular for his activity related to, I would say, mathematical cardiac electrophysiology, which is also the title of the book he has authored some years ago. And his activity focuses on the design and the analysis of scalable solvers, preconditioners, domain decomposition methods, with several applications to cardiac bioelectrical activity and cardiac electromechanics. So today, we will talk about scalable solvers for cardiac electromechanics and applications to arrhythmogenesis in LQT8 syndrome. So please, Luca, the stage is yours.
Thank you, Andrea. Thank you for this kind of introduction. Thank you for the organizer, for this opportunity. Do you hear me fine? It's okay?
Yes, from my side, yeah.
Also, the slides are coming up. Let's see. Are they visible?
Yes.
Okay.
You have, yeah, now in full screen, fine, thanks.
Perfect. Okay. So this would be a talk, the first part would be more numerical, and then you will see some application to particular rare disease stemming from a collaboration. So this joint work with Piero Colli-Franzone from the University of Pavia still, and Simone Scacchi from the University of Milan. Let me just review first, briefly, the main cardiac models that we're going to consider to build our solver. So of the three cardiac functions, the three main cardiac functions, the electrical, the mechanical, and the fluid dynamic, we are going to consider mostly the first two. So let's start with the electrical one. Our model consists at the macroscopic level in the bidomain model, or its a simplification, the monodomain model, which is a reaction diffusion PDEs for the intracellular and extracellular potential and how they evolve in space and time in the cardiac tissue. And the cardiac tissue is considered orthotropic, and there is a fiber structure, as you have seen in several talks before. And this is coupled at the microscopic at the cellular level with the membrane model, which is an ODE system of that describes this evolution of the gating variables. Let's say call them W, and ionic concentrations C, which are necessary to describe the ionic current. Then we have on the mechanical side, at the microscopic level, we have the model of passive mechanics, which are the classical PDEs on nonlinear elasticity that describe the cardiac deformation. Again, here the tissue is considered orthotropic and is almost incompressible, and the deformation are large, no small deformation. And the system is coupled at let's say the microscopic level with a model, again an ODE system for the so-called active tension TA. And you can see all these four submodels are all coupled with each other. Here just showing some of the main coupling. Okay, so well, we can see them later. And there will be also the third component of the cardiac function, the fluid dynamics, but so far we have only the PV loop, which gives some pressure boundary condition to the passive mechanics. We do not have yet the fluid dynamic component and the fluid structure interaction that would be needed to describe also the fluid. So a little bit more in detail. So the bidomain model, you can see here the equation in the simple formulation, the so-called parabolic is called, consists of two reaction diffusion equation. It's a degenerate system because the time derivative is on the transmembrane potential, V, which is the difference of UI and UE, and therefore the two potentials are defined up to a constant. That makes the system singular and harder to solve numerically. And then there is the ionic term, the reaction, which depends on V, the gating variable W, and the ionic concentration C, which are ruled by this ionic model. And here there's a whole library of models developed over the decades. They all stem from the Hodgkin-Huxley formalism from the 50s. And then we have considered like many groups in the world. For example, there is the Lurudi family for guinea pig, or for human ionic model, we use mostly the Tentasher, either 04 or the 2006, or the Arrhythmogenesis. While for a bit more in detail, the mechanical model consists just on the equilibrium equations, which are just the divergence of the stress tensor is 0 on the deformed body. You can also write it on the undeformed body. And there appears this the second Piola-Kirchhoff stress tensor. And we model it in the so-called active stress formulation, where the stress is seen as the sum of a passive component, an active component, a volumetric component. Well, the passive component here is just like a Hodgkin, Holzapfel and Hodgkin orthotropic law, the exponential energy function. As we said before, this is coupled to the active tension subsystem. And for this one, we use a system dates back to a paper by Land et al. 2012, which consists of 4 ODs. And the active tension TA here depends on the calcium, intracellular calcium concentration, the stretch lambda, and the stretch rate. There are several other models. These are just some modeling choices. Okay, so then when you write all this system together, coupled, it sort of emerges that this complex system is able to take into account the so-called mechanoelectric feedback, and the electrical bidomain system, here you can see, becomes the one that is written here in the slides, and where the mechanical deformation affects the electrical part in 3 main ways. The first one, you can see it here, is the diffusion coefficients, the conduction coefficient are changed with this deformation gradient tensor F, and its determinant J. It appears this kind of formulas. Then there could be also, that's another modeling choice, a convective term that depends on the velocity field of the deformation field. I didn't write it here. It is not used much in the literature. And then, very important, the ionic current is augmented with a stretch-activated current, ISAC, which depends on V and the stretch. And this is due to the fact that some channel gets activated by when the tissue contracts or relaxes, I mean, when there is a stretch. So then we take this model and we discretize it. We use a Q1 isoparametric finite elements in space. This is again another choices. Another choice what could be used at P1 unstructured finite elements, but we chose this because structured meshes lead to faster solver. We use the library PETSI, which in turn offers some object, DMDA, to treat structured meshes. And in time, we use some splitting and IMEX techniques. So for example, if we are at time n, we have all the quantities at time n. So first we solve the membrane model with a first order IMEX method. And we compute the new gating variables, W, and ionic concentration C, in particular the calcium concentration. Then we solve in a couple ways, as you have seen in some previous talks, the active tension and the mechanical model. So we can get the new coordinates, x, time n+1, and also the new deformation gradient and the active tension. Then we solve finally we solve the bi-domain system once we have all the other variable, and we update the electric potentials, UI, UE, and their difference. So this leads the discrete level to some larger discrete system. So for the mechanical one, this is nonlinear. There's because the PDEs are nonlinear. So we need to use a Newton method as outer iteration, and at each Newton step, the Jacobian system is solved with a GMS method, iterative, one of the Krylov solvers. It has to be preconditioned in order to get an efficient iterative solver. And we use either algebraic multigrid or some method of the domain decomposition family, which comes from the parallel solvers community, and one particular one called BDDC, balancing domain decomposition by constraints, which is available in this library PETSI. The electrical system, the bi-domain system, or monodomain if you use the simplified one. This is linear instead because we use IMEX, implicit-explicit decoupling. In this formulation also is symmetric, so we can use a conjugate gradient. It's a semi-definite, so we just need to be careful to stay in the kernel, in the orthogonal of the kernel of the system, and you can use PCG. And again, preconditioning is essential to go fast, and we use a Schwarz, overlapping Schwarz preconditioner, or again this BDDC. Both are domain decomposition. So the library I've seen is, as I've said before, is PETSI with some MPI and IPRE. We need to go parallel because the mesh that come up in 3D are pretty large. So the computational platform we use are some local parallel cluster, either University of Milan or Pavia, or some large machines at the Supercomputing Center. Either we have used Mira at the Argonne National Lab or Marconi here in the Italian Cineca Supercomputing Center. And let me just show you then some of these results quickly. We'll review what we have done in the last few years. So this, for example, is a so-called weak scalability, so which is a thing that is of interest from a parallel computing viewpoint. It is to test the solver by keeping the local size constant on each processor, and we increase the number of processors and increase the total global size proportionally, so that if the method is a good one, it's scalable, then we should be able to do this in a constant time, above constant, or at least with an upper limit. And this is what happens here. So you can see that when we go from 1,000 processor to 163,000 processor, all the mathematical quantity and the time, meaning the condition number is the blue dots, they stay sort of stable. So here the problem size grows from a few 100,000 to 600 or 700 million unknowns. Also the iteration remains stable, and also the time in seconds. Except the last, there's a little increase past 128,000 processors. So these are the machine where we have run this, the Mira. This is the one at Argonne National Lab. And this is Marconi. They're both by now dated machines. And Marconi should be soon replaced by a new machine next year, Leonardo. The mechanical system is the mechanical solvers instead is more challenging. Here you can see some run we have done on another machine at KAUST, the Shaheen 2 machine. Here's a slightly, this is the local size kept fixed, okay, both electrical and mechanical. And here I don't report the Newton iteration because they are constant, either between 4 and 6 iteration. And we look at only at the linear iteration, and is again a weak scaling. Now is the other domain decomposition solver called BDDC. And we go from 256 processors to about 16,000. And these are two domains, two different geometry, one simple slab domain or an ellipsoidal domain mimicking a monoventricular geometry. And these three are three different variants of the preconditioner, technical using vertices of the subdomains or vertices and edge averages or edge and face averages. Anyway, are three stronger versions of the preconditioner, of course, also more costly. What I want to point out is that the solver is scalable with this preconditioner. You can see that the iterations remain bounded, okay? In all the three versions for the slab and all the three versions for the ellipsoidal, much higher, much harder due to the formation of the geometry. And anyway, they are scalable. And the timing, and not so much if the processor count starts increasing. So it is some work still needed here, okay? And here then we applied also to some simulation of reentry in later publication in Chaos 17 and Frontiers 18 and Mathematical Bioscience. So for example, you can see here that we started with a cross gradient protocol, a set of two counter rotating spirals. And here on top we have two tests with a slow, let's say, with a weak stretch activated current. At the bottom, a stronger stretch activated current in this mechanoelectric feedback. And on the right, instead, is without the geometric feedback. And here there is totally on the left, on the right, there is the complete mechanoelectric feedback. And you can see that these spirals are stable. If there is a weak stretch activated current, while they become unstable in the other case, showing that is a big determinant, the stretch activated current. Okay, just now we are working on better nonlinear solver for the electrical component. And there is a PhD thesis in progress by Monica Mai Huyn here in Pavia. And also we are working on better mechanical solvers using the LifeX parallel library that you have already heard mentioned in this workshop. And this is joint work with Quarteroni's group. We have a project by an Italian print project. And in particular, we are collaborating with Christian Vergara, Luca Dede, Pasquale Africa, that you will hear tomorrow, is also in the coffee break, about the LifeX, and Nicolas Barnafi. Now, in the remaining time, I would like to show you some application to this LQT8 or Timothy syndrome. LQT8 is just a cardiac manifestation. So this is part of the Timothy syndrome peak project by Silvio Priori at the University of Pavia and also Margeri Institute. And is the first knock-in model of long QT syndrome in a swine strand, actually in a large mammal. And so far, it is an ongoing project. So this Timothy syndrome, TS, is a very rare disorder, which has also extracardiac manifestation. Particularly, there's physical malformation, neurological and developmental defects. The syndactyly, which is like a webbing of finger and toes, autism is a terrible disease. And the poor children that get it, the average age of death is 2.5 years. At the cardiac level, it manifests in long QT syndrome, which is classified as LQT8 when it comes from the Timothy syndrome. And this leads very often to death. Okay, they are very strong defects. So these are just some images to show you what these things are. So in A, you see some example of a syndactyly, and then also facial dysmorphism here on top. And here you can see in the precordial leads in B, you can see some the T-wave alternance, some of the manifestation, and the remarkable prolongation of the repolarization. The ST segment is often straight. There's a small regular T-wave, and another example of probably 2-1 atrioventricular block due to this extreme QT prolongation. So what has been discovered? That this Timothy syndrome is caused by a mutation in this CACNA1C gene, which is the one encoding this CAV1.2 subunit of the L-type calcium channel. So it's a mutation of the alpha subunit of the L-type calcium channel. You can see a schematic representation here. And then if you zoom inside this alpha-1 unit, which is the channel pore, see here, you can see that it is made up with 4 homologous domains. Each one has 6 segments. S1 is 6. And there are several mutations that have been discovered over the years. Here, I just show the main one in black. And what we concern is this one, the G406R. Okay, this mutation. There are several. You can, for example, in the Zipes and Jalif, the cardiac electrophysiology book, there are listed more than 20 mutation of this gene. And we will focus on these two, which is basically, they are very similar. One leads to Timothy syndrome TS1, which has also this syndactyly problem, and the other is Timothy syndrome 2 without syndactylity, but both are terrible cardiac variants. They affect 2 different exons. And so this is just as a cartoon. This is how it works. This mutation causes a loss of inactivation in the L-type calcium channel here. So this remains this inward current instead of getting inactivated. You can see it here in B. This leads to a prolonged action potential, and this can lead to early after depolarization or delayed after depolarization, which lead to defibrillation or other kind of arrhythmias, tachycardia or fibrillation. And we follow in particular the work by Splavsky, which was the first to study this kind of mutation. Before there were no other mutation of those 20s. And here from his paper, you can see that his results in the wild type cell, the inactivation is normal. With a mutation, with a G406R mutation, there's a lot of current remaining. And of course, the voltage current curves then are quite different. You can see the wild type here in bullets gets inactivated at a certain voltage, and instead the mutated one, no, remains like this. And similar, okay, with a barium current, but it is secondary. And there's also another paper by Yazawa and other in Nature in 2011 that using stem cells, the induced pluripotent stem cells, they showed that the presence of this mutation induced DID here. You can see it in this is the mutated cells, action potential here. We have the control one without DIDs. And also in the calcium transient, here on the right, they showed me here the control, here the mutated one, Timothy syndrome. And here they are more irregular, this transient, and also with larger amplitudes, significantly more. You can see here in this box plot. Okay, so how do we model this thing? There are several possibilities and several details, but the main one that I want to tell you about is that we need to modify the steady state F infinity of the slow inactivation gate F of this L-type calcium current. So we modify this as follows. Here we take the midpoint voltage V, I, and A of the inactivation curve, and the slope S, I, and A of the inactivation curve, and they are modified between the wild type and the mutated one. This would base this on the experimental results reported by Splasky, either in the paper Cell 204 or in the PNS subsequent paper in 205. And then I want to show you just some simulation. Okay, so we do a stimulation protocol, which is known S1, S3, S4, S1, S4. Like in Priori's group, they do it experimentally. And so first we do 8 pacing beats at 500 milliseconds as basic cycle length. And then we give an S1 at 500 milliseconds, S1 stimulus, endocardial. And then an S2 is given just after the S1 refractoriness. So we need to test a few times. If nothing happens, you increase by 10 milliseconds interval. You increase till you see front propagating. And you take the shortest of this interval. If there is a re-entry, so it's sort of, in a sense, it's closer to the vulnerable window. If there's no re-entry, then you repeat with the S3, same thing. You go as close as you can to the S2 refractoriness. If there is a re-entry, fine. If not, repeat again with an S4. If there is no re-entry, in this case, stop. We, like a priori, experimentally, we don't continue, we don't insist. We also consider a transmural heterogeneity with three, let's say, 3 areas within the wall, the cardiac wall, by scaling the IKS current by certain factors. And we consider a 50% heterozygosis in the mutation. And these are the results. So first, let's consider the wild type. We do it without heterogeneity. So there is the S3, now there is the S4, endocardial. It's just a nice propagation and nothing happens, that's it. So then we start introducing the transmural heterogeneity. And this is the S3, comes the S4. There is something like after the polarization, but it's not enough, it's too early, and still nothing happens. There's no re-entry, is triggered. So then we tried okay. Then we try with the mutated now case. We introduce 50% mutant mutation, and still we do not have the transmural heterogeneity. So we can start this one. You can see S3. Then we give the S4. And there is something that starts later, but it's not enough to trigger. Now I cut it short, but we run everything for 2 seconds, and there's nothing. There's really nothing here. While if we no, next one, yeah. If we start introduce both the mutation and the transmural heterogeneity, then we obtain we trigger a re-entry. So this is 4, and now we don't beat anymore, but you can see that starts now this the polarization that starts later is enough to propagate, and it keeps going. Here we even run it to 4 seconds to make sure that it was sustained, and it is sustained. And this is, in a sense, now we are working to compare with this, some data from Priori's group, which they also found that it is not easy to induce with this protocol tachycardia of this type, or eventually even fibrillation. And here, to understand it a bit better, the importance of the transmural heterogeneity combined with the mutation, we can do also some sections. And you can see here, if we cut in the 2 directions, circumferentially here and longitudinally, you can see that the effect of the M cell here is, in a sense, crucial. The difference in APD, or if you want to call it a transmural gradient of repolarization, is crucial, see? Because after the first 2, well, that's S3 and S4, exactly is this kind of re-entry appears here and re-enters transmurally. Okay, you can see it also here in the circumferential way. And then it becomes stable. Okay, so let me conclude, since we started late, I'm trying to make up some time. So in conclusion, by now we know that it's possible to do large-scale 3D cardiac simulation. This is due to several advances, for sure in the machine that are continuously improving, also in the libraries that are improving. We hope to get some benefits also from LifeX, of course, and from solvers. I've shown you some, in particular, I focus on the solver here. And the solver that we found most efficient in this kind of simulation, large-scale parallel simulation, are the so-called domain decomposition solver of both family, the multi-level Schwarz with overlap, or the one without overlap, or dual primal type, in particular the BDDC. These are available both for the bidomain, for the lexical, and for the electromechanical, but more work is needed for the mechanical solver. And in general, to get better non-linear domain decomposition solvers. That is, as I mentioned before, is one of the focus of this PRIM project with Quarteroni's group. And in the application that I just show you to LQT8, to this Timothy syndrome, here we saw that these mutated L-type calcium channels plus the transmural heterogeneity are the main determinants for generating sustained re-entry. And of course, we are collaborating, and there's work to do to compare with clinical data from Priori's group. And we hope to, in the future, to come up with a more complete picture. So thank you for your attention.
So thank you very much, Luca, for your extremely interesting lecture. I guess that several people concerned with either software implementation for electrophysiology or applications in electromechanics will have questions or comments. So the floor is open for questions, comments, or remarks. So I see a raised hand by Professor Flavio Fenton.
Yes, hi, Luca. Very nice presentation.
Flavio.
Good to see you. So very impressive solvers you combine together. So one of the examples you show for the solver is the contraction and how the fibrillation changes when you include the effect of the contraction and the mixing with the stretch activated channels. However, one of the things that we have to be careful, I guess, when we're comparing is just because sometimes we can create something different doesn't mean exactly that is physiologically correct. Experimentally, when you add, when you do an experiment and map the voltage, the fibrillation on a rabbit heart or a pig heart before you, with contraction, and if you will prevent the contraction with something like brevistatin, the arrhythmia remains basically the same. So not exactly is the stress activated channels and the contraction that changes the dynamics a lot. So that's one of the things that we have to, I guess, consider. I think sometimes when contraction is included, one thing that we don't include in the modeling is the use of oxygen. And the faster you contract, the less oxygen is available to the cells, and then that becomes actually a little bit more ischemic. So that's probably one effect that we need to include when you do contraction and include it for fast pacing.
Okay, thank you. Thank you for the comment. Yes, completely agree. Yes, there's more factors to be included, and more work to be done to find out precisely these different determinants in these cases. Yeah. This was a sort of just a sort of preliminary study that we sort of put together. Yes.
Sure. And just one quick question at the end. For the LQT8, did you try to reproduce the T-wave alternance and the QRS alternance that you observe, that is observed in the clinic with your model?
No, not yet. No, we didn't try that. And also first we just focus on how to trigger this with this protocol as S1 S4, because it's not it's very time consuming. You know, each test is a run. Then you need to run it for long to see if there is a re-entry or not, if it is sustained or not. And it's not like just starting with a cross gradient or with other kind of stimulation. It is very time consuming. So that's what we focus so far.
How long it takes to do one simulation? Roughly a couple of weeks.
Well, it depends. If we go, let's say we can go with a monodomain or the bidomain. That's a big the big difference. If we go with a monodomain, is only a few hours to do this 2 seconds. If you go with a bidomain, is more than 10 for sure, more than 10 hours.
Great. Thanks, Luca. Thanks so much.
You're welcome.
So I also see the hand raised by Professor Natalia Trajanova. So Natalia, please. I think you have to turn your microphone on.
I don't hear, yes.
Yeah. Natalia, can you hear us? Well, if not, I thank Natalia. No, I think she cannot hear us.
No, we don't hear. We can talk tomorrow at the coffee then, in case.
Yeah, I think so. So if there are no further questions, let us thank again Luca and all the speakers